So in example 2, we are again looking at our old friend, the vector field F that is rotating around the z-axis where in every plane parallel to the xy plane. And we already seen it a couple of times, and we have imagined placing our pedal wheel inside this vector field with the handle pointing in different directions, and we saw that depending in what direction we pointed that handle, we got different values for our circulation and also for our circulation density then. And sometimes it was clockwise, sometimes it was counterclockwise, and sometimes it was 0. Now, the new question is, how would I have to place my pedal wheel so that the circulation density appears to be the greatest? So, abstractly, for what value of normal vector n does the circulation density at 0, 0, 0, so still right in the middle right here, appear to be the greatest? So not just positive, but also as big as possible. We already know that if we stick the handle parallel to the y-axis in this direction right here, we get 0. When it was pointing straight up, we had positive circulation. When it was pointing straight, so up was positive, down was negative. We saw that in example 1, or rather in the preliminary example. And we didn't really look too much what happens when we are pointing in directions other than straight up, down, or in the direction of the y-axis, but you can imagine that we could do that as well. And now the question is, which of those directions would give us the greatest circulation density? Okay, I'll let you think about that while I'm erasing. Well, the twirling is going around this way, so you can imagine that if I put in my pedal wheel so that the pedals get pushed the most, my handle is sticking straight up. And so that would give me the greatest rotation of my pedal wheel. And so I get the greatest circulation density when n is equal to k. And it's definitely positive. We already checked that out. So now we are ready to talk about the geometric definition of the curl. So in a previous section, you already learned all about the coordinate definition of curl. So you already know how to compute it. If you have a vector field F that has an I component F1, and J component F2, and a K component F3, then you can compute the curl of that vector field as partial F3 partial Y minus partial F2 partial Z in the I direction, plus partial F1 partial Z minus partial F3 partial X in the J direction, plus partial F2 partial X minus partial F1 partial Y in the K direction. And we had a better way to compute that using a determinant right here. And so you've already done that. So you know how to compute the curl given a vector field. But what does it mean? Well, the curl of a smooth vector field F, written curl F, we know that, is itself a vector field. And it has two important properties. The direction of the curl at any point, x, y, z, is the direction of the normal vector n for which the circulation density is the greatest. So just as we saw in example 2 above, that if I pick a point, I can stick that pedal wheel in different directions, and I get different circulation and different circulation density depending how I stick in n, in what direction n points. And only one of those directions is going to give me the greatest circulation density. And so that will be the direction of curl F. So that gives me the direction of a vector curl. What is the magnitude of the vector curl F? That is the circulation density of F around that direction. So again, the curl of a vector field, curl F, is a vector field itself. So it's a vector field itself that has two properties. One is the direction of curl F is a direction that gives me the greatest circulation density, and then the magnitude is this circulation density around the direction.